Hey everyone, welcome to Math 172. My name is Blake Whitley. I'll be your instructor for this semester. Hopefully you've had a chance to go through the Blackboard site now and kind of find your way around and figure out where things are. If you have any questions about where any of the assignments for this week are located, please let me know. Also, if you're having any issues getting into WebAssign, please definitely let me know that also so we can get that resolved. If you have questions about any of the due dates, let me know. But today we're going to get started with section 6.1, angle measures. My plan is to actually do a video for each of the sections that we're going to cover, and those will be posted in the course content folder. That way, if you have any questions about how to do any of the examples from the homework or anything that's on the quizzes, you can refer back to these videos to see how to do some of these examples. If you have any questions beyond that, please let me know. You can definitely come see me during my student hours. If those times don't work for you, please email me and we can try to find a time that works a little bit better for you. All right, so without further ado, let's get started with section 6.1. Okay, so the first thing we're going to look at here is what we call an angle. Okay, so we need to define what an angle is. So an angle is going to always consist of two rays that meet at a single point, which we call the vertex. So in this angle that's given here, AOB, O is your vertex, and then you have ray OB and ray OA that form this angle. Now, every angle is going to have an initial side and it's going to have a terminal side. And what we mean by that is the initial side is where we're going to start our measurement from, and the terminal side is where we end our measurement. So if you notice the angle on the left-hand side there, we're starting from ray OA and we're measuring around to ray OB. Because we're measuring in a counterclockwise direction, the opposite direction of the way a clock would run, we call that a positive angle measurement. Okay, so when we measure that angle, if it's counterclockwise, we're going to have a positive angle measure. On the other hand, the angle on the right, our initial side, OA, if we measure around to OB, we're actually measuring in a clockwise direction now, and so that angle measure is going to have a negative measurement. Now, one of the units we're going to use to measure our angles is what we call degrees. That's probably the one most people are familiar with. There are 360 degrees in a full revolution, so 1/360th of a revolution is equal to 1 degree. Now, on the next slide, we're going to look at the other type of angle measure that we're going to use a lot this semester and how it's related to those degrees. And so if a circle of radius 1 is drawn with a vertex at the center of your circle, the angle measure for that central angle is going to be equal to the radian measure around the arc length of your circle. Okay, now what this basically means is if you draw your angle and it intersects the circle, that arc length that's shaded in red there is going to be equal to whatever that central angle measure is, as long as the radius of your circle is 1. That's the key here. If the radius is something other than 1, then we're going to have formulas to determine how big that arc is. Okay, but as long as the radius is 1, that arc length is going to be equal to whatever the angle measure in radians is at the center of your circle. Now here's the relationship between degrees and radians. Okay, so we know 180 degrees is going to be equal to pi radians. Remember, pi is just an irrational number, approximately 3.14, but we are going to use an exact value of pi. So whenever you're doing these calculations using a calculator, please use the pi symbol in your calculator, not just the approximation, because we want to get as accurate as we can. Now, because of this, since we know 360 degrees is a full revolution around a circle, if we were to convert this now, we can basically just double the number of radians since we're doubling the number of degrees there. And so 2 pi radians is going to be 1 full revolution around your circle. Okay, so 180 degrees would only be halfway around, 360 degrees goes all the way around. So pi radians is halfway around, 2 pi radians goes all the way around. Okay, and then you can see these conversions that we have here. So to go from degrees to radians, we're going to take our degrees, we're going to multiply by pi over 180, and that'll take us from degrees to radians. If we want to go from radians to degrees, we're going to take our radian measure, we're going to multiply by 180 over pi, and that'll convert to degrees for us. All right, so our first example here, we want to express 60 degrees in radians. So notice we're going from degrees to radians. So if you remember what we saw on the previous slide, we're going to take that 60 degrees, we're going to multiply by pi over 180. Now, when I do this, I'm going to think of these both as fractions, which means I can just multiply straight across. So I'm going to write this as 60 over 1. When I multiply straight across, that's going to give us 60 pi over 1 times 180 is just 180. And then we always want to simplify our fractions. So notice here we have a common factor of 60. And if I divide the numerator and denominator by 60, that's going to give us 1 pi over 3. So in this case, this is pi over 3 radians. And so we want to write RAD just to indicate that that is a radian measure now. Now, if we want to go the other direction and go from radians to degrees, we're going to take our original radian measure, pi over 6, and this time we're going to multiply by 180 over pi. And now this time we already have two fractions, we can just multiply straight across. So that's going to give us 180 pi over 6 pi. And as always, we want to simplify our fractions. Notice here the pi in the numerator and denominator should just cancel out. And so we're really just dividing 180 over 6. And if we do that, that should give us 30. And now we convert it into degrees. So just make sure you use your degree symbol to indicate that that is a degree measurement now. So that's how we convert from degrees to radians or from radians to degrees. All right, now angles in standard position. Whenever we talk about standard position, that means that our initial side is going to be the positive x-axis. And so notice here, all of these angles that are drawn, A through D, are all measured from that positive x-axis, either in a clockwise or a counterclockwise direction. Now, any two angles in standard position are what we call coterminal if their sides coincide. So if you look at these, A and C are what we call coterminal angles. And the reason for that is, even though angle C goes all the way around and then a little bit more, it still ends in exactly the same position as angle A. And so we call those two angles coterminal angles now. Now, what that means is if we're looking for coterminal angles, we can actually just take an angle measurement and we can add a full revolution or subtract a full revolution to find any angle that would be coterminal with it. And we already talked about the fact that 360 degrees is a full revolution, or if you're dealing with radians, 2 pi radians would be a full revolution. Okay, so example 2, we want to find angles that are coterminal with the angle theta equals 30 degrees. Okay, so make sure I mention this symbol here because this is one we will see a lot. Okay, so we read that as theta. It's a Greek symbol. It's just like an X or a Y in your pre-calculus classes in the past. We're using that to represent some variable. Okay, so we're letting our theta equal 30 degrees here. And so this time, if we want to find something that's coterminal with that angle, I'm going to take my 30 degrees, and remember we said we can either add or subtract a full revolution. So I'm going to add 360 degrees, which gives us 390 degrees. And so a 390 degree angle would be coterminal with a 30 degree angle because it's just one additional revolution on top of that. It would still have the same starting position and ending position. Now we can also subtract a full revolution from the given angle. So I'm going to take 30 degrees. I'm going to subtract a full revolution of 360 degrees, which is actually going to give us negative 330 degrees. So negative 330 degrees would also be coterminal with a 30 degree angle. And there will be times in the homework where you ask to find like two positive angles that are coterminal, two negative angles that are coterminal. So just be sure either add or subtract to find those positive or negative angles. And now the second part of this example says we want to find angles that are coterminal with an angle theta equal to pi over 3 radians in standard position. So this time we're dealing with radians since we have pi over 3. And so remember, we're going to add and subtract a full revolution. This time, though, because we're dealing with radians, a full revolution is going to be 2 pi radians. So I'm going to add 2 pi. And to be able to add these things together, we need a common denominator since I'm dealing with a fraction here. So I'm going to change this to pi over 3 plus, and to have a common denominator of 3 here, this is going to be 6 pi over 3. Okay, because 6 pi over 3 would be equivalent to 2 pi. Now that we have a common denominator, now we can just add. And remember, to add fractions, we add the numerators. So that's 7 pi. Keep the common denominator. So that's 3. And this is now in radians. So 7 pi over 3 radians is coterminal with a theta value of pi over 3 radians. And again, if you're looking for a negative angle, all we have to do is subtract 2 pi. So I'm going to take pi over 3, subtract a full revolution of 2 pi. Again, we need that common denominator. It's still going to be the same thing though, 6 pi over 3. And now when we subtract, we just take the numerators and subtract. Pi minus 6 pi is negative 5 pi. Keep your common denominator, 3. And again, that is in radians. So negative 5 pi over 3 radians is coterminal with pi over 3 radians. All right, number 3. So we're going to find an angle with measure between 0 degrees and 360 degrees that's coterminal with the given angle of 1,290 degrees in standard position. So notice here, 1,290 degrees, definitely larger than 360. We want to find an angle, though, that's coterminal with it, that's somewhere between 0 and 360 degrees. So remember, to find coterminal angles, we can either add a full revolution or subtract a full revolution. Since our angle's too big to begin with, we're going to want to subtract a full revolution. So I'm going to take 1,290, and I'm going to subtract 360 degrees from that. Now, when I do that, that should give us 930 degrees. Now, notice that's still too large, okay, which means we're actually going to need to go even further than that. So what I'm going to do next is I'm going to subtract another full revolution. I'm going to take 930 degrees. I'm going to subtract 360 degrees. And when I do that, that should give us 570 degrees. And again, that's still too big because we need something between 0 and 360 degrees. So I need to subtract off another full revolution. So we're going to take 570 degrees, subtract 360. And in this case, that should give us 210. And 210 is between 0 and 360 degrees. So 210 degrees is our coterminal angle with the given angle of 1,290. So anytime you're looking for an angle that's between two angle measures, usually they're going to ask you for something between 0 and 360 because that's a full revolution. You're either going to have to add 360 or subtract 360, and sometimes you'll do it multiple times depending on how large or how small the given angle is. All right, now the length of a circular arc. So we already talked about that as long as your radius is 1, the theta value should be equivalent to whatever that arc length is. Well, now we have a formula that says, well, no matter what the radius is, we can find that arc length by taking the radius, which is r, and multiplying by that central angle, which is theta. Notice here, though, this theta has to be in radians. Okay, so that's key. If they give you degrees, we have to make sure we convert first. Do not multiply radius times a degree measure. That won't work. Okay, so always convert to radians first unless you're already given radians to begin with. Okay, so S represents the arc length, R is your radius, theta is the central angle, and it has to be in radians. All right, so we want to find the length of an arc of a circle with a radius of 10 meters that subtends a central angle of 30 degrees. So just to kind of give ourselves an understanding of what we're looking at here, I'm going to draw a circle. I'm going to draw our central angle, which in this case is 30 degrees. And so we're looking for, if the radius is 10, what is this arc length right over here? Okay, and again, the central angle is 30 degrees. Now, to find this, again, our formula has to be in radians. So we need to convert that 30 degrees to radians first. So I'm going to take my 30, I'm going to multiply it by pi over 180. Again, change this to 30 over 1 so that it's a fraction. We can multiply straight across. So we get 30 pi over 180. And now when we simplify that, 30 goes into both 30 and 180. And so we get pi over 6. Okay, so there's our radian measure now. And our formula said we can do S equals R times theta. So now all we have to do, arc length should be equal to the radius, which is 10, times that central angle in radians, which is pi over 6. And now if we multiply that, again, I'm going to write this as 10 over 1, so we can multiply straight across. That should give us 10 pi over 6. And again, we always want to simplify. 2 actually goes into both of those numbers in the numerator and denominator. So that's going to give us 5 pi over 3. Now, units are going to be really important for us. So we have to think about what we actually just found. This is not a radian measure. It's really easy to think that it might be because it has a pi in it. But remember, what we were finding is the actual arc length. So since we're looking for a length of something, it's actually going to be measured in the same units as whatever the length was in the problem. That was meters. So this is actually 5 pi over 3 meters is the length of that arc that's subtended by that angle. All right, now the second part here says a central angle theta in a circle of radius 4 meters is subtended by an arc length 6 meters. We want to find the measure of theta in radians. So this time, again, I'm going to draw my picture just so we know what we're looking for. So there's my circle. We know the radius here is going to be 4. I'm just going to draw some angle. Radius of 4. We don't know what that central angle is, so I'm just going to put theta there. But we're given the fact that the arc length is 6 meters this time. So I know the length of this arc along the outside of the circle is going to be 6. So now I can use that same formula that we used before, S equals R times theta. But this time we know the arc length, so we know S, so that's going to be 6. We know the radius, that's 4. And we're looking for our theta value. We're looking for the angle itself. So now to solve for theta, all I need to do is divide by 4 on both sides. So that's going to give me my theta. And now if we simplify 6 over 4, again, 2 goes into both of those numbers. So that's going to give us 3 over 2. And again, we just need to make sure that we're thinking about our units here. Since we actually found a theta value, and we know theta in this formula has to be in radians, this is actually going to be 3 over 2 radians. And you might be thinking to yourself, well, wait a minute, all the radian measures we've done so far had a pi in them. That's true. They don't have to, though. Okay, so 3 over 2 radians is an actual radian measure. Don't just assume that because there's no pi in it that it can't be a radian measure. Just like before on part 1, we had 5 pi over 3. Just because there's a pi doesn't make it a radian measure. That was actually a length. All right, now the area of a circular sector. Okay, so sector is basically like a slice of a circle. It looks like a slice of pizza. Okay, so anytime you're looking for the area of a sector, we're going to use this formula. A equals 1/2 r squared times theta, where theta has to, again, be measured in radians. All right, so we want to find the area of a sector of a circle with a central angle of 60 degrees if we know the radius of the circle is 6 meters. Okay, so again, I'm going to sketch my picture here so we know what we're looking at. We have a central angle, 60 degrees. And we know that the radius here is 3 meters. And this time we're actually looking for what's the area of that sector. Now, again, first thing we need to do is we know our theta has to be measured in radians to be able to use this formula. So I'm going to go ahead and convert 60 degrees, multiply by pi over 180. That should give us 60 pi over 180, which simplifies to pi over 3. And so now we know our theta, and so now we can go to our formula. Area equals 1/2 r squared times theta. And we substitute. So we have 1/2. R this time is our radius is 3. We're going to square that value. Then we're going to multiply by the theta, which we just calculated, pi over 3. I'm going to go ahead and simplify some of this. Remember, order of operations says we would do our exponent first. So that tells us we're going to do 1/2 times 3 squared is 9 times pi over 3. And now we just have all multiplication. And so I can just write this as 9 over 1, multiply everything straight across. So we have 1 times 9 times pi. That's going to give us 9 pi. 2 times 1 times 3 is going to give us 6. And now we can simplify that fraction because 3 goes into 9 and 6. So that gives us 3 pi over 2. And again, we need to think about our units. And in this case, we actually found the area of something. Remember, our linear units that we're given were in meters. So if we're looking at an area, this is actually going to be meters squared. So just always think about what did you actually find and what would the units have to be for that thing that you're looking at. Since we're finding an area, we know it's going to be a squared unit. And in this case, the units were meters, so it's going to be meters squared. All right, now circular motion. So with circular motion, we have two types of speed. We have both a linear speed and an angular speed. Linear speed is the rate at which the distance traveled is changing. So whenever you're calculating a linear speed, we're going to take the distance and we're going to divide by the time. And if you think about it, if you're driving a car, linear speed would be like miles per hour. Miles being your distance, hours being your time. You're taking miles and dividing by time. Angular speed, on the other hand, is the rate at which the central angle is actually changing. So if we're moving in a circle, we're actually going to have a rate at which that angle is changing, that central angle. And so to find that, we're going to take the number of radians and we're going to divide by the amount of time. Okay, so it's going to be radians over time is going to give us an angular speed. Now notice at the very bottom here, we have angular speed. We're going to use this W symbol to represent that. Linear speed, we're going to use V for like velocity to represent that. And so our W is equal to theta, which is the angle, divided by the amount of time. Our V, linear speed, is going to be S, which is the arc length. And we can use the same formula we used before to find that. And we're going to divide that by the amount of time. All right, so our next example says a boy rotates a stone in a 3-foot-long sling at a rate of 15 revolutions every 10 seconds. We want to find the angular and the linear speed, velocity, of that stone. Now, the first thing I want to find is that theta value. So we know we're going to need that to be able to find angular speed for sure. And it's also going to help us in our linear speed since we're going to need to know the arc length. So to find our theta, here's what we've got to think about. We know that the stone is traveling 15 revolutions every 10 seconds. Well, 15 revolutions, we know a full revolution is going to be 2 pi. So I'm going to take 15 revolutions, multiply by 2 pi, which is going to give us 30 pi radians as our theta value. So whenever you're given a number of revolutions, just remember one full revolution is 2 pi. So if you multiply the revolutions times 2 pi, that'll give you the number of radians. Now that we have that, we can actually calculate our angular speed. So angular speed, remember, is going to be theta divided by time. This time our theta is 30 pi. I'm going to keep my units here, so that's radians. Our time is 10 seconds. I'm going to divide by 10 seconds. And the reason I kept my units here is because that's going to help us with the units of our final answer. So when we divide 30 pi by 10, we can actually divide both of those by 10. That's just going to give us 3 pi. But our units now are going to be radians per second. So I would always suggest, keep your units throughout the problem, and then that'll make the final answer units a little bit easier to see. All right, now the other thing we're asked to find is linear speed. So remember that formula, V equals S over T. Now, we don't know the S value, but we do have a formula that we can use to calculate it. So I'm going to come over to the side and I'm going to find that. So remember, S equals R times theta. Well, our radius is actually going to be the length of that sling, right? Because if you're standing at the center and you have a sling going out and you're rotating it around, the length of that sling is the radius of your circle as it moves in a circular motion. So R is going to be 3. Theta we already calculated is going to be 30 pi. And so that's going to give us 90 pi. And notice here our units, since we're looking at an arc length, that's actually going to be in feet, since our radius was measured in feet this time. And now if we go to calculate our linear speed, we're going to take that S value that we just calculated, 90 pi feet. We're going to divide by the amount of time, which is 10 seconds. And when we divide 90 pi by 10, that should just give us 9 pi. And again, our units, we have feet per second. So our linear speed this time, 9 pi feet per second. All right, and then finally we have a relationship between our linear and angular speed. So if you know one, you can actually find the other. And the way we can do that is by just taking linear speed is equal to the radius times the angular speed. All right, so our final example for this section, a woman is riding a bicycle whose wheels are 26 inches in diameter. If the wheels rotate at 125 revolutions per minute, we want to find the speed, in this case in miles per hour, at which she is traveling. Okay, now, again, the first thing I want to do is try to figure out what our theta is going to be. So since we're given a number of revolutions, we can say theta is equal to 125 revolutions times 2 pi, since each revolution would be 2 pi. And when we do that, that should give us 250 pi radians. Now, if we want to find the angular speed, W is equal to theta over time. We just calculated theta, that's 250 pi radians, over time, in this case, is actually just 1 minute, right? Since it was 125 revolutions per 1 minute, this is just going to be 1 minute, which means when we divide this, we're just going to get 250 pi radians per minute. Now, what we're trying to find is actually the linear speed, because we just want to know how fast is this woman traveling on this bicycle. But we know now that we have a relationship between angular and linear speeds. Linear speed is r times w, so the radius times the angular speed. So we need to know the radius, we need to know the angular speed. We just calculated angular speed. The radius here, we just have to be careful. Since we were given diameter is 26 inches, that means radius is actually going to be half of that. And so our radius is actually 13 inches this time. So just be really careful. Even though 26 inches is what's given, we need a radius. So make sure you cut that diameter in half to get the radius. So now we're going to have V equals 13 times 250 pi. And when we do that, I'm actually going to get this as a decimal value now because we're going to have to do some converting. And rather than dealing with the pi, I just want a decimal. So when you do this in the calculator, you should get 10,210.2. And now we have to think about what our units are. Okay, so notice here that radius was measured in inches and our time was measured in minutes. So this is actually going to be inches per minute. Now, that's not what we were asked to find. We were asked to find the linear speed in miles per hour. So our last step here is to actually convert those inches per minute into miles per hour. So I'm going to take the 10,210.2 inches per minute. And when I do conversions, I always multiply. That way I never have to worry about, well, am I multiplying to go one direction, dividing to go another direction? I just always set up a fraction and try to cancel out my units, and that way I can always multiply. I'm going to multiply. Now the first thing I'm going to try to convert is those inches. So we know we want to go to miles. Now, I don't know the exact conversion to go straight from inches to miles, but I do know how to go from inches to feet. So I'm going to put my inches on the bottom so they cancel out, and I'm going to put feet on top so that I end up with feet. Now, I know for every 1 foot, there's exactly 12 inches. So I'm going to put 1 foot on top, 12 inches on the bottom. And by doing that, I'm canceling out my inch unit. So now if you look at what's left over, we have feet over minutes, so feet per minute. Still not what we want, right? But we're getting closer. I'm going to multiply again. Now I'm going to convert from feet to miles because I do know how many feet are in 1 mile. Again, I need to cancel out feet, so I'm going to put those on the bottom. I need to end up with miles, so I'm going to put those on top. And I know that for every 1 mile, there's 5,280 feet. And by doing that, I've canceled out my feet units. And so now I end up with miles over minutes, so miles per minute. Still not quite what we want, but I at least have the linear unit correct, right? I have it in miles. So now the last thing we need to do is convert those minutes into hours. So again, I'm going to multiply. I need to cancel out my minutes, so those need to go up top. I need to end up with hours, so I'm going to put that on the bottom. And I know for every 1 hour, there are 60 minutes. And now because I have minutes on top and bottom, I can cancel out my minutes. And so now I'm left with miles per hour. And at that point, we just have a whole bunch of fractions, which we know we can just multiply straight across. And so if we do that, that should give us 612,612 over 63,360. And now if we divide that, now I'm just going to round this to one decimal place. Should give us approximately 9.7 miles per hour. So again, I always start by finding that theta value, right? If they give you a number of revolutions, then we can use the theta to help us find the angular speed. From angular speed, we can find linear speed, and then just always pay attention to what units they want for their final answer. Sometimes you might have to do some converting. And if you have any questions about conversions, right, obviously you can Google a lot of those, but if you need help with converting, please let me know. I'm more than willing to give you those conversions also. All right, so that's everything we've got for section 6.1. Again, I'll be adding more videos as we go, so please be looking for those. If you have any questions, let me know, and good luck on the homework.